Achilles, the fastest runner in ancient Greece, races a tortoise. The tortoise is given a 100-meter head start. Common sense says Achilles will overtake her in seconds. A philosopher in southern Italy, around the year 450 BC, proves it is mathematically impossible. By the time Achilles reaches the spot where the tortoise started, the tortoise has crawled forward a little. By the time Achilles reaches that spot, the tortoise has crawled forward again, and again, and again. To overtake the tortoise, Zeno argues, Achilles must complete an infinite number of catch-up tasks in a finite time, and that, he says, is impossible. For 2,500 years, the best minds in philosophy could not really refute him. Zeno of Elea was a student of Parmenides, founder of the Leibniz school of philosophy in southern Italy. His original writings are lost. We know his arguments only through reports, chiefly from Aristotle, who recorded them about 100 years later in his book Physics. Zeno's purpose was not to win a race. It was to defend his teacher's claim that motion itself is illusion. To defend that claim, Zeno designed arguments to show that the opposite belief, that motion is real, leads to absurdities. The rules of the Achilles paradox are three. Rule 1. Space is infinitely divisible. Between any 2 points, there is a third point, always. Rule 2. Time is infinitely divisible. Between any 2 moments, there is a third moment, always. Rule 3. No finite agent can complete an infinite number of distinct tasks in a finite span of time. 3 rules. 2 of them feel obvious. 1 of them feels like common sense. Watch what happens when you run a race against a tortoise. So, Achilles starts at 0 meters. The tortoise starts at 100 meters. Achilles runs at 10 meters per second. The tortoise crawls at 1 meter per second. Step 1. After 10 seconds, Achilles reaches the spot where the tortoise started, 100 meters. But in those 10 seconds, the tortoise has moved forward to 110 meters. Step 2. Achilles closes the new 10-meter gap in 1 second. He reaches 110 meters, but in that second, the tortoise has moved forward to 111. Step 3. Achilles closes the new 1-meter gap in 1/10 of a second. He reaches 111 meters. The tortoise is now at 111.1. The pattern continues. Each step, the gap shrinks by a factor of 10. But each step, there is still a gap. To overtake the tortoise, Achilles must complete every one of these steps. There are infinitely many of them. Each takes non-zero time. By Zeno's third rule, no agent can complete infinitely many distinct tasks in finite time. The conclusion follows. Achilles can never overtake the tortoise. And yet, anyone who has ever watched a race knows that he does. The argument is wrong somewhere. For 2,000 years, nobody could say where. The first instinct is to say, but obviously Achilles catches up. The argument must be wrong. That instinct is correct. The argument is wrong. But pointing at the catch is not a refutation. Zeno is not denying that Achilles catches up. He sees it too. What he is denying is that our description of motion as a sequence of first reach this point, then that point, is coherent. To refute Zeno, you have to do something harder. You have to explain how an infinite sum of decreasing distances and decreasing times produces a finite total. For 2,000 years, nobody had the mathematics for this. Aristotle, around 350 BC, made the first serious attempt. He drew a distinction between potential infinity, a line that can be divided indefinitely, and actual infinity, a line already divided into infinitely many completed pieces. Zeno, Aristotle argued, was assuming the wrong one. It was clever. It was not enough. Aristotle could not show how the infinite sum of vanishing distances corresponds to a finite total. He simply asserted that the divisions were not all there at once. For 2,000 years after Aristotle, no fundamentally new analysis appeared. In 1665, an English mathematician of 23 was sent home from Cambridge because of plague. His name was Isaac Newton. While at his family farm in Lincolnshire, he invented the method of fluxions, what we now call calculus. A few years later, in Germany, Gottfried Wilhelm Leibniz invented the same mathematics independently. Newton and Leibniz did not set out to defeat Zeno. They were trying to describe planetary motion in the area under curves. The defeat of Zeno was a side effect. Calculus introduces a single concept that Aristotle did not have: the convergent infinite series, the infinite sum, 1/2 plus 1/4 plus 1/8 plus 1/16, and so on forever, adds up to exactly 1, not approximately 1, not arbitrarily close to 1, exactly 1. The sum is finite, even though the number of terms is infinite. Apply this to Zeno. Kill. Easy closes the gap in steps of 10 seconds, then 1 second, then a tenth of a second, then a hundredth. The sum of all those times, infinitely many terms, equals exactly 11.11 repeating seconds. At the 11.11 second mark, Achilles overtakes the tortoise. The math gives the exact moment. 200 years later, in the 1860s, Carl v. Weierstrass formalized the limit concept rigorously. The dissolution of the paradox was now provable. Calculus tells us how the infinite sum converges. It does not tell us whether the infinite sum physically happens. When Achilles runs from one point to another, does he really pass through infinitely many positions? Or is space, at the bottom, made of indivisible units below which further subdivision is meaningless? Modern physics has not settled this. The smallest length scale at which our current physical theories break down is called the Planck length, about 10 to the minus 35th of a meter. Some physicists working on loop quantum gravity argue that space-time below this scale is genuinely discrete, built of indivisible chunks. Others argue space-time is continuous all the way down. If space is genuinely continuous, calculus is the answer, and Zeno was beautifully wrong. If space is genuinely discrete, Zeno's first rule is empirically false, and the paradox dissolves for a completely different reason. In 1977, two physicists named Mies Ra and Sudar Shun derived a quantum effect now called the quantum Zeno effect. A quantum system under continuous observation does not evolve. Constant measurement freezes motion. They named it for Zeno because the structure mirrors his arrow paradox, and because his question, 2,500 years later, is still alive in physics. The mathematics of the paradox was closed in the 1820s. The physics is still open in 2025. Bertrand Russell, writing in 1903 about Zeno, gave him a defense that no philosopher of 2 millennia had thought to give him. After 2,000 years of being treated as a clever sophist, Russell wrote about Zeno's 4 arguments, in plain quotation, 4 arguments, all immeasurably subtle and profound. Russell's point was simple. The philosophers who dismissed Zeno as merely a juggler had not noticed that he had identified a real gap in our concept of motion, a gap that took the invention of calculus, set theory, and rigorous limit theory to fill. The arguments were not sophisms. They were the cleanest way ancient philosophy had of pointing at a problem that ancient philosophy could not yet solve. Zeno's paradox did not break mathematics. It pointed at a missing piece of mathematics and waited. What is motion really? Is it a smooth flow through a continuous medium, or is it a sequence of discrete jumps through indivisible quanta of space and time? The answer changes the meaning of every physical law. We have the math, we do not yet have the physics. The runner crosses the finish line. The philosophers are still arguing about how he got there. Achilles raced a tortoise. A philosopher proved he could not overtake her. A finishing tape said he did. 2,000 years later, calculus explained how. 2,500 years later, the deeper question, what motion really is still open. Every week, another paradox, another impossible idea that turns out to be true. Subscribe. The next one might break something you did not know you believed.